Welcome to The Explainer. Today, we're diving deep into a comprehensive research report all about a material that is quite literally secretly powering everything around us. I'm talking about everything from the crowns on your teeth to the roaring jet engines soaring thousands of feet above your head. We are talking about Zirconia Ceramics, and I am so pumped to get into this with you because this isn't just your everyday run-of-the-mill ceramic. It's actually a high-performance, shape-shifting super material that completely defies everything we normally assume about brittle ceramics. Okay, so right off the bat, let's shatter a very common myth. When you hear the word zirconia, your mind probably jumps straight to those cheap, fake diamonds you see at the jewelry store, right? Well, we really need to separate cubic zirconia from engineering zirconia. The gemstone version, sure, it's optically clear, it's hard, but it's basically a fragile single crystal with absolutely zero toughness. If you hit it, it shatters. Engineering zirconia, on the other hand, it is an indestructible structural super ceramic. It uses this amazing stress-induced toughening and can handle extreme temperatures that would literally melt steel. So yeah, it's a completely different beast. All right, now that we've cleared that up, here is our roadmap for today. First, not just fake diamonds. Next, we'll look at its shape-shifting superpower. Then, from sand to ceramic, followed by extreme properties and powers, real-world applications, and we'll wrap up with the future of zirconia. Let's get into it. Not just fake diamonds. So, what exactly is this stuff at a molecular level? Well, pure zirconia, or zirconium dioxide, is a polymorph, and that just means its crystal structure physically changes its shape depending on the temperature. At room temperature, it sits in a monoclinic phase, heat it up to 1170 degrees Celsius and it shifts into a tetragonal phase, push it all the way up to 2370 degrees and it becomes cubic. Now the problem here is that these transitions cause the material to expand and contract. In a solid piece of ceramic, that expanding and contracting would normally cause it to just crack into pieces as it cools down. So to fix this, scientists use this brilliant chemical magic trick. They mix in stabilizer oxides, things like yttria, magnesia, or calcium oxide. These dopants essentially freeze the high-temperature tetragonal or cubic structures, locking them in, so they stay perfectly stable even when you bring the material back down to room temperature. That brings us to section 2, the shape-shifting superpower. This is how it beats brittleness. You see, depending on exactly how much of that stabilizer we add to the mix, we get totally different identities for the material. If we add just a tiny bit of yttria, like around 3 mol%, we get TZP, or tetragonal zirconia polycrystal. This stuff is ultra-fine-grained and has absolutely massive toughness. But if we use a bit more of a stabilizer, say magnesia, we get PSZ, which stands for partially stabilized zirconia. This one mixes cubic and tetragonal phases to give you extreme resistance to thermal shock. And finally, if we flood the recipe with, say, 8 to 10% yttria, we get FSC, fully stabilized zirconia. This is mostly cubic. Now, it loses its crazy toughness here, but it gains incredible ionic conductivity, which is a neat party trick we'll talk about in a minute. But going back to TZP and PSC, why exactly are they so unbelievably tough? It all comes down to a phenomenon known as transformation-toughening. By carefully engineering the ceramic, scientists leave those tetragonal grains in what's called a metastable state. So they're sitting there perfectly comfortable at room temperature, but they are just waiting for any excuse to pop back into their larger monoclinic shape. And when physical stress hits the material, like, say, a crack trying to form, that stress actually provides the exact burst of energy needed to trigger that transformation. Let's visualize how this works in real time, happening in a fraction of a millisecond. Step 1. Stress is applied, and a microscopic crack starts to propagate through the ceramic. Step 2. The intense energy concentrated right at the tip of that crack acts as a trigger. It causes those local metastable grains to instantly shift from tetragonal back to monoclinic. And when they do this, they physically expand in volume by about 3 to 5%. Step 3. This sudden, highly localized expansion acts exactly like a microscopic airbag, inflating inside the solid ceramic. It physically squeezes the crack shut, puts it under immense compressive stress, and stops it dead in its tracks. The material literally shapeshifts to save itself from shattering. I mean, how cool is that? Okay, let's move on to section 3, from sand to ceramic. How do we actually manufacture this stuff? Creating this super ceramic is honestly an epic trial by fire. It starts out super humbly as zircon sand, which is usually extracted from heavy mineral beaches in places like Australia. This cheap sand gets put through intense chemical digestion to strip away impurities like silica, turning it into a highly pure chemical precursor. Next up is powder milling, where it's broken down into impossibly fine, sub-micron particles. Those powders are then mixed with organic binders and formed into shapes through dry pressing, injection molding, or even cutting-edge 3D printing. Finally, this green part is fired, or sintered, in a massive furnace at staggering temperatures up to 1600 degrees Celsius to reach its full, dense, final form. And what's really wild here is the level of extreme precision required during that sintering phase. As that powder densifies into a solid block, the zirconia shrinks by a massive 20 to 25%. Engineers have to account for that shrinkage perfectly. But even more importantly, the exact temperature and the amount of time in the furnace dictate the final size of those microscopic grains. If it sits in the heat for too long, the grains grow too large. And if that happens, well, the grains might just spontaneously transform while cooling down, causing the whole piece to self-destruct. Or they'll lose their transformation-toughening superpower entirely. It is a crazy, delicate balancing act. Section 4. Extreme properties and powers. Let's look at the stats. 1300 degrees Celsius. Just to put that into perspective for you, unless you're making a habit of hanging out inside an active volcano, that is unfathomably hot. But because zirconia has incredibly low thermal conductivity, meaning it is a fantastic insulator, fully stabilized zirconia can comfortably operate as a thermal barrier coating. They literally spray this stuff directly onto the metal turbine blades inside roaring jet engines and gas power plants. It protects the structural metals underneath from temperatures that would absolutely melt them into a liquid puddle. Now, this number, 10 to 20, is the Weibull modulus of high-grade zirconia. In engineering circles, the Weibull modulus is a statistical measure of reliability. Usually, ceramics are notoriously unpredictable, right? You could test 10 identical ceramic plates, and they might all break at totally different force levels just because of random microscopic flaws. But a Weibull modulus of 10 to 20? That proves zirconia is exceptionally consistent and predictable, and that is a very rare, very prized trait for any ceramic material. So to quickly summarize its extremes, high-grade TZP can hit a flexural strength of up to 1.2 gigapascals and a fracture toughness of 7 to 13 megapascal root meters. That absolutely dwarfs standard ceramics like alumina. It's strong, it's hard, it's highly insulating. However, we do have to impartially note its one real Achilles heel: low temperature degradation, or LTD. In hot, highly moist environments, water molecules can slowly trigger that phase transformation at the surface over time, and that leads to microcracking and aging. Now, modern engineering has largely mitigated this by tightly controlling the grain size, but it's a factor engineers always have to keep in mind. Actually, scratch that. Physical strength isn't its only superpower. Remember that fully stabilized zirconia we talked about earlier? By flooding the recipe with 8 to 10% yttria, scientists don't just freeze the cubic structure, they actually alter the atomic lattice itself. They create these missing spots called oxygen vacancies. So at high temperatures, oxygen ions can rapidly hop from vacancy to vacancy right through the solid ceramic. This transforms the material from a standard heat insulator into a fast oxygen ion conductor. It essentially becomes an electrical component. Which perfectly segues into Section 5, Real-World Applications. Let's see this in action. In the industrial and energy sectors, zirconia's sheer toughness means it makes amazing wear-resistant cutting tools that can slice right through solid steel. It's also used for highly durable bearings and pump valves that resist chemical corrosion. Its thermal properties make it the gold standard for those thermal barrier coatings on turbine blades we mentioned. And thanks to that unique oxygen ion conductivity, it is the primary electrolyte used inside solid oxide fuel cells for generating clean energy. It's also the active element inside the lambda oxygen sensors in your car's exhaust system, constantly measuring emissions in real time. Over in the biomedical field, zirconia is an absolute game changer because it is perfectly inert and totally biocompatible with the human body. Dentists use it constantly for crowns and bridges. They'll actually balance the ultra-strong 3Y TZP for your back molars where you need maximum bite force with slightly weaker but much more translucent, natural-looking 4Y or 5Y TZP for your front teeth. On top of that, orthopedic surgeons rely on composites like zirconia-toughened alumina for things like hip implants. It provides an incredibly smooth, low-wear joint replacement that won't ever release metallic ions into your bloodstream. And finally, Section 6. The future of zirconia. Where are we heading next? Well, you know researchers are never fully satisfied. Today, they are tailoring zirconia at the absolute nanoscale. By combining advanced nanostructuring with co-doping techniques, basically mixing in new elements like cerium or scandium alongside the yttria. They are developing experimental ceramics that are pushing fracture toughness well beyond 20 megapascal root meters. We are literally approaching a threshold where this ceramic could realistically rival the toughness of some metals. At the same time, the explosion of additive manufacturing, 3D printing, is allowing engineers to print highly complex, customized, patient-specific lattice structures that were completely impossible to machine even a few years ago. So, that leaves us with one final provocative thought. We started this journey with cheap Australian beach sand. We chemically engineered it to harness a microscopic, shape-shifting phase transformation, and we turned it into jet engine heat shields and indestructible replacement body parts. If we can 3D print perfect, highly durable teeth and hip joints today, what kind of world will Zirconia build tomorrow? I really hope this explainer gave you a newfound appreciation for the incredible science hiding right under our noses in the ceramics all around us. Keep learning, keep questioning, and I'll see you in the next one.